Everyone, in the last class we talked about Bitcoin NG, which tries to increase the throughput on the blockchain. But we saw that there were many issues with the Bitcoin NG, and we said we would talk about something called Prism, which tries to increase the throughput but without having some of the problems that Bitcoin NG had. Right? But Prism does much more than increase the throughput. It also increases the chain stability. Let's talk about the chain security. And before getting into the details of Prism, I wanted to talk about this topic a little bit. So let's revisit some of the issues with Bitcoin. So we said that each of these blocks has proof of work. And if we plot against time, sometimes the blocks are generated fast and sometimes it takes long to generate. It's essentially a random process. And this is an issue which Satoshi himself showed. What did he show? Well, he did a double spend analysis. And he showed that an attacker could create maybe a chain of his own, which is, let's say, longer than this particular chain, and then release it. So because of these random generation times, these random instants, even if the hashing power is more on this honest chain, the attacker might get away because he might be lucky that his random process generated let's say four blocks, whereas here there were only two, for example. Right? So with some probability this private chain attack is going to work just because these blocks are generated randomly. Okay, and this comes from proof of work. Okay, it's sort of inbuilt. So this is one issue, I'll just write it over here, that blocks are generated at random time instants and it allows things like double spend attacks. Another issue is network delays. So what is the issue here? Well, it takes some time for blocks to propagate in the network. So there is the speed of light propagation. And then of course there is the validation time. So we said that every honest miner is supposed to validate a block before forwarding it. Okay, because if you don't do that, then you're unnecessarily flooding the network with possibly invalid blocks. Right? So if a block is large, let's say 1 MB or even higher than that, it takes a little bit of time to validate the block. Right? And so the network propagation delays could be as high as 10 seconds, let's say. For Bitcoin. So because of this 10-second delay, it's possible that even honest miners might generate blocks so as to create a fork. Right? So you have a block here. So too many honest miners are trying to mine on this block, and within a period of 10 seconds, let's say both of them generate a block. So each of them has not seen the other's block, so both release their blocks, and we end up with a fork. So this is both are created by honest miners. So this is an issue because I mean it wasn't considered in Satoshi's original analysis because he didn't take network delays into account. But the problem here is that you don't know which is going to be there. So there's ambiguity in the chain. Right, so nobody knows which is going to end up. So if my transaction is in this block and not in that one, should I believe that it's there in the blockchain or not? Right? And also it could lead to orphaned blocks. So one of them is going to win out and one is going to lose out. So orphaned blocks, and that would mean wasted hashing power. So somebody has successfully generated a block, but that hashing power is not recorded in the longest chain, and he doesn't get any reward. Let's say his hashing success is not recorded in the longest chain. Okay, and because, so first of all, it's a little bit unfair to a miner. He's put in a lot of effort to mine the block and he doesn't get a reward. But this other issue is also affects the security of the blockchain, in that it's easier for an attacker to perform an attack. So it's easier for a double spend attack. Right, because suppose the attacker wants to build a private chain which is longer than the main chain. Suppose he forks from here. So how many blocks does he need to have a chain longer than this one? So suppose this was a linear chain, he would have needed 3 blocks to be longer than that, but here he needs just 2 because each of these is of length 1. Right? So 2 blocks are enough to be longer than the honest chain. Right? So these sort of natural forks are a problem, which is why of course Satoshi made the interarrival time to be 10 minutes between blocks, so that the chances of 2 people generating blocks within 10 seconds of each other is somewhat small. Once in a in a very rare instant, you may have these sorts of natural forks happening in Bitcoin. But the flip side of actually having blocks spaced far apart is that your throughput goes down. Right? You have hardly 7 transactions per second possible with Bitcoin. Okay. So these are some issues which related to security, and one is caused due to these random generation times. Essentially you can model it as an exponential arrival process, I mean effectively a Poisson arrival process, because the interarrival times are exponential. And in addition, the network delays are an issue. They cause forking, which have their own security problems. Okay. So what I want to do now is to think, can we do this proof of work in a different way, or even if we stick to proof of work, can we do things differently in order to reduce some of these problems? Okay, and maybe some of you might have ideas of your own of how to do proof of work, but in general, if you're flipping a coin every time to find out whether you are within the target space or not, you will end up with some sort of a Poisson arrival process. Right? But the question is, what can we do here? Uh, let's just think aloud and we'll see maybe what is possible. So one idea is let's generate blocks faster. Okay, so instead of let's say having the block generation times, suppose the blocks are generated here and so on. Let's say that the average time is 10 minutes. Okay. Can I generate them faster, and maybe this might resolve some of the problems? Okay. So suppose and really what do we want to do? So it's see, the thing is we have this proof of work space, and let's say that here I have 2 to the power of 256 minus 1. So there is some target space we are trying to find by doing our hashing, and we really want to have some idea of how much hashing is being put on which chain, right? So that's sort of what we have at the back of our mind. So if we go back to this situation, suppose I knew that 90% of the hashing power was on this block at the top, then maybe I could switch there right away. Okay, but the way Satoshi does it is you don't know how much hashing is happening on each block, so you just wait for a new block to be created on one of these, and that sort of indirectly tells you, let's say, which particular block more people were hashing on. Okay, roughly. Okay, but of course it's possible that with a small probability even the block which had less hashing power on it gets extended first. That may happen. Right? But this whole idea is that Satoshi is signaling how much proof of work is there in the network by the generation of blocks. Okay, so Satoshi of course has solved too many things in one shot. So POW is contained only in blocks, and that comes somewhat slower. Okay, so suppose you have a fork like this, it might take 10 minutes for this fork to get resolved, right? Because a block takes roughly 10 minutes to be generated on average. So we might think, what if I generate blocks faster? It might be a naive idea, but let's see what happens. Suppose I generate blocks, let's say every 1 minute rather than every 10 minutes. Then maybe the block will come within 1 minute and I will be able to resolve this fork faster. Okay, so that's sort of the first idea that we are thinking of. Let's generate the blocks faster. And what our hope is that a natural fork will get resolved faster. Okay, so if you have a fork like this, the next block comes within 1 minute, suppose. Okay. So this seems to be a good idea, but what is the flip side? The flip side is that you might create more forks. If you generate your blocks faster, you might actually create some extra forks like this. Of course, you might be able to resolve them, maybe, it depends, but it's possible that these forks keep getting extended too. You may have, let's say, one block getting generated here and so on, right? So more forks may be generated in the first place. Okay. But of course, if we neglect network delays, then of course it makes sense to reduce the spacing between blocks, because you don't have any natural forks. And if you if you generate blocks faster, effectively you will be signaling the proof of work faster, and you might be able to make it harder for somebody to do a double spend attack. Okay. So let's write that down. If there are no network delays, there are no natural forks. So by natural fork, I mean if everybody is honest, you might still have a fork. These are created by honest miners. So then reducing block interarrival time makes sense. And why is that? Because Satoshi's analysis tells you that if you have, let's say, 6 blocks, okay, so these are the conformations. So Satoshi looked at this analysis where the attacker is generating blocks, and he said that once you generated 6 blocks, after the, let's say, this particular block which was forked out, so this is where the transaction is, and if you generate the 6th confirmation, he said, with some high probability, this particular block is going to be there forever, right? And if you neglect network delays, you just have to count the number of blocks. It doesn't depend what the speed at which you're creating blocks are, whether it is 10 minutes between a block or not, right? So if I suppose reduce the block interarrival time from 10 minutes to 1 minute, then the 6 blocks are generated in 6 minutes, okay, and you would have 6th confirmation in 6 minutes. Right, so maybe if there are no network delays, it makes sense to reduce the interarrival time, because you don't have to deal with natural forks, and you get your 6th confirmation faster, and Satoshi's analysis holds, right? Everything works out fine. Okay. But of course, then you might say there are no network delays, why not make your block interarrival time almost 0, right? And of course that it doesn't make sense to do that in practice, because there are network delays, right? So, but of course in a very abstract setting where there are no network delays, this might make sense, but in a real world, just reducing the interarrival times has its own issues. So if this idea of generating blocks at a faster rate has flaws, is there any other way to do proof of work in order that we can deal with these problems, right? So what we want to do is we want to make the chain more secure in some way. We want to make attacks like the double spend attack become harder to do. Okay. So let's keep the idea of generating blocks faster, but let's think about it in a slightly different way. So suppose we wanted to generate blocks faster, what do we do? So this is the target space. And let's say this is the normal target space. What do we do if we want to generate blocks faster? Well, we just increase this target space, right? So that for a larger range of hash values, we have some valid proof of work which we can send out to the rest of the net, right? So if we just have a single threshold like this and we generate blocks, then we see that we run into some problems. Even though we are adding blocks faster, those blocks may end up creating forks, more forks in fact, because we are sending out the blocks closely spaced to each other. So how can we do it differently? So suppose we have this target space. Suppose we think about it in a very slightly different way, and right, so this is 0, this is 2 to the power of 256 minus 1, and this is, let's say, the initial target for a block. Let's have a second target. Okay, so instead of having a single target, let's say T1 and T2. And let's say that if the hash falls in this space, we say that a certain type of entity is created. I'll just call it entity 1. And if the hash value is within this range, we will call it entity 2. Okay. So any hash value, if it lies between T1 and T2, then we say entity 2 is created in some way. Okay. So how is this going to help? And let's actually look at a real example. And this was work of one of my students, PhD student Sovya Seshadri. Okay, and she has 2 papers on something called anchors and links. Okay, one paper is on anchors and the other on links. So what is an anchor? So just let's go back to Bitcoin. So we have a block header, and in Bitcoin we have something like this. So we have transactions. These are the regular transactions, and there is a separate Coinbase. Okay. And the structure is something like this, right? So this is just a hash. Okay, so you combine let's say the Merkle root of the transactions, and you take the hash of the Coinbase, and you get the final Merkle root which you put in the header. Right? So this is these are non-Coinbase transactions. And what we normally do is we are changing the nonce value. Let's say this is the nonce, and we wait till the block header value is less than a particular threshold. So let's keep the threshold the same for the blocks. T1 is the block generation threshold. Right? So we keep hashing away just like you would do in normal Bitcoin. And if the hash of this header is less than the threshold, then you generate a block. Okay. Now what we are going to say that if the hash of the block header, okay, so it is less than t1, we say that a block is generated, and if it is between t1 and t2, then we say that an anchor is generated. So what is an anchor really? And we want to use whatever we have created in some way in the blockchain. Okay, so what is an anchor? So in an anchor, we don't transmit the full block. So if anchor is generated, then drop the transactions, okay, except the Coinbase. So you drop this whole thing, and the remaining part, the header and the Coinbase, is essentially the anchor. And what a miner does is that he transmits this anchor, he broadcasts it into the network. Okay. So you see the mining process is happening as it is, as usual before. And normally if the hash value was larger than T1, we wouldn't bother at all. But here, when the hash is in a different range, we say that we have created an anchor, and we drop all the transactions in the block, but we send out the header and the Coinbase. Okay, so this Coinbase is just there so that you can reward the miner in some way, right? So we have to reward people for creating blocks, but we also want to reward them for creating anchors. So the miner broadcasts this anchor. And what is good about this anchor? So first of all, this anchor is small in size. And in Bitcoin, the header is hardly 80 bytes or so. It's very, very small compared to a 1 MB block. So the anchor is small, so it propagates very fast in the network. Okay, so it could be just 2 to 3 seconds compared to 10 seconds for a block, for 1 MB block. Right? So this is a very good property that let's say that when somebody generates an anchor, he sends it out very quickly, the rest of the network gets to know about this anchor. Okay, so you can use this as a fast method to give information to people about which blocks people are mining on. Okay, and let's see what are other good properties. So let's actually show you how, let me show you how exactly the blockchain looks when we have anchors. So these are blocks. And these are generated as usual, like in Bitcoin. And suppose everybody is mining on this particular block. Let's say somebody generates an anchor, not a block. Right? So remember that this block header is pointing to the previous block. It has a pointer to the previous block. So when an anchor is generated, it will also point to one of these, and just draw it this way. Okay. And let's say that one anchor was generated on this block, and let's say another person also generated an anchor here. Right? And this could keep happening. If it takes longer for a subsequent block to be generated, more and more anchors are sent out, and people will receive these anchors pointing to various blocks. So there could be an anchor pointing here also, for example, right? Something like this. And there could be any number of anchors pointing to a block. It all depends on how long it takes for somebody to generate the next block. And now let's say somebody generates another block here. So what is the advantage of these anchors? Well, remember that previously when we had only blocks, the chain weight was increasing every time a block was generated, and that could be 10 minutes apart for Bitcoin, but it also might be 15 or 20 minutes, right? Because it's a random process, and maybe the block interval time can be large. But now with anchors, what is happening? You're releasing these anchors as and when they are generated, so the chain weight keeps increasing faster. Okay, so how do you calculate the chain weight? So weight of block, okay, let's write the weight of an anchor. Okay, so we want to give a weight proportional to the proof of work done, right? So the weight of a block should be proportional to T1, and weight of an anchor should be proportional to T1, T2 minus T1. Okay. So if you want, if T2 is much larger than T1, effectively it's very easy to generate an anchor. The anchors are generated much quicker, but correspondingly they will have less weight. Okay. And how do we decide on the weight of a chain? So weight of a chain is equal to sum of weight of blocks plus sum of weight of all anchors on blocks which are in the chain, right? So for this particular chain I would have to add the weight of all these blocks, plus I am adding the weight of the anchors. Okay. So effectively what we are doing here is, I should say point number 2, a good point is that anchors add weight to the chain steadily. Okay. So more steadily, that you can say, compared to blocks. Okay. So suppose I had a blockchain, and this was the weight of the blockchain. Every time I had, let's say, a block generated, I would increase by, let's say, a block weight, whatever it is, and that could be erratic. It might look something like this, right, depending on the block generation instance. Now suppose I have anchors in the picture, right? So let me show that in a different way. So suppose I had an anchor, let's say this first block was the same, right? And then let's say after some time I got another anchor and so on. right? And let's say that the blocks were generated at the same time instance, right? So I got a jump here, but then let's say I got few anchors, I got another jump, large jump here, right? And so on. And here of course I don't have anchors. Okay, so with the anchors, the weight of the chain increases more steadily. So essentially this anchor is conveying some information to the other miners. It's telling everybody in the network who are miners, which block miners are actually trying to mine on. Okay, so suppose I had a situation. Let's go to the next point over here. Okay, and I'm going to claim that anchors can resolve forks faster than blocks. Okay. So this earlier point which I discussed in point 2, where I'm increasing the weight steadily, this is clearly going to help in a double spend attack. Okay, and why is it? Because in a double spend attack, if the blocks were generated far apart, the attacker had an advantage. He might actually be able to generate more blocks than typically his hashing power would correspond to, and the honest people have taken a long time to generate a block, so he might be able to succeed in a double spend attack. Here weight is getting added steadily. Even when you don't have a block generated for a long period of time, anchors are being generated in the background, so they keep adding weight to the chain steadily. Okay, so that makes the task of a double spend attacker harder. Okay, and we'll see, in fact, in our paper we have proved that that is indeed the case. Okay, so how can we resolve forks faster than if you just had blocks? Let's say block only chain. So suppose we had a chain and maybe we had some anchors here, right? Maybe here there was only one anchor, right? And the rule for creating these anchors, the rule for mining on a chain is always that you should mine on the heaviest weight chain. Okay, so let me write that down. Always mine on the heaviest chain. Okay. So this is what is happening over here, and let's say that we had a fork over here. Okay. Now how is the fork going to get resolved? So normally you would have to wait for the next block to come, and that could be 10 minutes of time, right, before this fork is resolved. Here let's say you get an anchor on this block. Okay, then automatically maybe this anchor comes in a few, let's say 1 or 2 minutes, right? And so what do all the miners do? Then everybody switches here. Right? And the fork gets resolved. Okay. So instead of it taking 10 minutes on average to resolve this fork, I'm going to resolve the fork maybe in a matter of minutes. Okay, and it all depends on how fast we are generating these anchors. Right? The larger T2 is, the faster I am generating anchors. Right? Another advantage over here of these anchors is that the anchors cannot create forks themselves. Okay. And why is that? Because the rule is a block only points to another block. And an anchor only points to a block. Okay. So as you can see that these two rules ensure that anchors cannot create a fork. You cannot have a situation where you have blocks, let's say arriving, let's say this is a particular block, and you can't have an anchor and you cannot have another block pointing to the anchor or another anchor pointing to an anchor. So this is not allowed. Okay. So anchors cannot create forks, although they add weight to the chain, they do not create forks, and that is an advantage. Okay, so it's not like there is a trade-off that they add weight faster but they can also create forks or something like that. Right? So this is an interesting idea, and the question is, how is it going to help? So let's write that down. Okay. So suppose we look at a double spend attack. And now you have, let's say this is the honest chain. Okay. And let's say that this is where there's a transaction is placed and the attacker wants to double spend this particular one. So the attacker is going to fork from an earlier block okay, and let's say that okay, suppose we are waiting for the sixth confirmation, 1 2 3 4 5 and 6. Okay. Previously, let's say suppose the attacker had a chance of winning of 10 to the power of -3. So suppose in the no anchor situation, we just had a plain blockchain. Suppose the attacker success probability is equal to 10 to the power of -3. Okay, and that's roughly the case when he has about 10% of the hashing power in the network. Right, so this is Satoshi's analysis, where when you wait for the sixth confirmation, the probability of the attacker catching up at some point in the future is going to be less than 10 to the power of -3. Okay. Now suppose we have with a situation where we allow anchors. So now what does it look like? Each of these could have anchors, and how many anchors are there will of course depend on various factors, because anchors too are generated randomly. Right? Maybe this one got 3 anchors. It depends on the thresholds you use, T2 and T1 and so on. Now you can see that by the time the 6th confirmation comes, there's also a whole bunch of anchors getting added. And even if the 6th confirmation takes longer, I mean, that's not such a big problem. I mean, though in the real world, I mean, it would be a problem when you don't have anchors, because if the 6th confirmation takes, let's say, 2 hours instead of 1 hour, the attacker has so much more time to create his own private chain. Right? So even if this comes 2 hours, let's say, instead of 1 hour in the future, there's a whole bunch of anchors on these blocks, and more anchors are generated over time. Right? So the chain weight, this particular honest chain's weight is going to increase more steadily over time. Okay? And of course the attacker also gets some anchors on his own private chain. Okay. But what we were able to show is that we actually are able to reduce the success probability by even a couple of order of magnitude. So I'll just say orders of magnitude reduction in the success probability. Okay, so that is for 6 confirmations. Okay, and this is also for 6 confirmations. So you might say, suppose I want a success probability of 10 to the power of minus 3 itself with anchors, and clearly 6 confirmations is a lot. I'm going to get orders of magnitude better. So can I have a fewer number of confirmations? And that's what we find. For a 10 to the power of minus 3 attack success, so this is with anchors, and of course the attacker hashing power is, let's say, 10%. So for a 10 to the power of minus 3 attack success, we need only 3 confirmations. Right, so just to be clear, if we stick with the 6th confirmation, which is, I'm saying that the person who's receiving money here, he waits for the 6th confirmation before believing his transaction is going to be there forever. Okay? Without anchors, you have to wait. I mean, you'll wait for an hour, right? For the 6th, roughly an hour for the 6th confirmation, and the probability of attacker success is 10 to the power of minus 3. If I have anchors in addition to blocks, and I wait for the 6th confirmation, that is, I wait for an hour, then the success probability of the attacker is much lower. It's something like 10 to the power of minus 5. Right? A couple of orders. You'll have to see the research paper to exactly get the exact number. I mean, it depends on different factors, but it's roughly a couple of orders of magnitude. Suppose I say that I want only 10 to the power of minus 3's chance of success of the attack, of this sort of a double spend attack. So I don't want to wait for the 6th confirmation. So what we are saying is, you wait only till the 3rd confirmation, which will come in about 30 minutes. So in about actually 30 minutes since the time you broadcast the transaction, or 20 minutes after this block appeared in the blockchain. Okay, so roughly you half the amount of time you have to wait to have the same confidence that your transaction will be there in the blockchain forever. Okay? And the reason is that these anchors are adding weight to the chain more steadily. Okay, so this is a clever idea, and so you might think, what is a drawback of anchors? So there is one issue, a very subtle issue, and especially it comes up when we are trying to analyze attacks. So normally in a blockchain, in a Satoshi type chain, if you're given a blockchain, you know the weight exactly. So in a chain with anchors, there is a slight difference. So these have anchors on them. Let's say that you have two anchors over here. Right? Suppose miner 1 sees these many number of anchors, he gets a particular weight for the chain. But suppose another miner, let's say, has seen a couple of more anchors. So even though they have seen the same set of blocks corresponding to the same chain, miner 2 sees a higher weight of this chain because he has happened to see these anchors, and let's say miner 1 has not seen these particular anchors. Okay? So there is a little bit of ambiguity, and it could be that these anchors are still propagating in the network, right? They are, let's say they haven't yet reached miner 1. That could be a genuine reason. So it could be that different miners might see different weights for a particular chain of blocks just because they haven't seen the same set of anchors on a block. Now this normally wouldn't be such a big problem when anchors are generated by honest miners, because they just broadcast those anchors and soon enough everybody gets to see those anchors, right? Whereas if an attacker tries to play mischief, he could in theory withhold his anchors for a long period of time, and that may allow him to perform some sort of an attack, right? So those sort of tricky situations have to be considered when we do a very thorough security analysis of these blockchains. Okay, but practically how would it matter? Well, suppose there was a fork over here, and suppose let's say these are the anchors that this is what miner 1 has seen, all the blue anchors, let's say, and miner 2 has seen everything. Now miner 1 thinks that this is the heaviest chain, so this looks heavier to miner 1, whereas to miner 2 this one looks heavier because there's 1, 2, 3, 4, 5, 6 anchors over here and only 5 over here. Okay, so even though both see all the blocks in both the chains, one thinks that one chain is heavier and compared to the other one, right? So these sort of tricky situations occur with anchors. Okay, so what we do, and of course if you think hard enough, you will come back with you will also come up with the solution of what we call links. So I'll just briefly talk about what links are. I think because the properties are very much similar to anchors. So again I generate links in this fashion. If the hash value is less than T1, then I say that it is a block. And if it is between T1 and T2, I say that it is a link. But now I let links become part of the chain. Okay, so I allow a link to point to a link or a block to point to a link. Okay, so the structure of the blockchain is a bit different, whereas anchors are sort of hanging from a block and sort of adding weight to it, which is why we give it the name anchor. Here these entities called links will actually be between blocks. So I may have another block generated here, right? It depends all on the random process, and it may happen that you have, let's say, a whole string of links getting added to the chain, right? So miners are continuously mining on the heaviest chain, and the weight of the chain is the sum of weight of all links and blocks in the chain, right? And of course we allow a block to point to a link. So block can point to block or link, and a link can also point to a block or a link, right? So the links are part of the chain, unlike anchors, and they have a lot of advantages, but also some disadvantages. So anchors, we said, cannot create forks, but links can create forks. Unlike anchors. But there is an advantage, is that a chain's weight is unambiguous. Okay. In this case, so given a particular chain, given all the entities in the chain, right, you can unambiguously say what is the weight of this chain. If everybody sees the chain, he knows exactly what the weight is. It's just like a typical blockchain. Okay? If you have a missing link somewhere, you really don't even consider that chain, because you need all entities in the chain in order for anybody to even consider it to be a valid chain. Okay? And so of course, analyzing the security properties of a chain with links is a bit easier than anchors, but the disadvantage is that links can create forks. So I could have, for example, another link pointing here, right? Or I can even have blocks pointing to links. I can have forks getting created here. Okay, so this is a disadvantage of links compared to anchors, right? So we have used these extra entities in a particular way, and it's sort of called a 2-for-1 proof of work scheme, where you're simultaneously generating links and blocks. You're not doing more proof of work. I should write that in bold. We are not doing more hashing. With anchors and links, right? So we just do the same amount of hashing as with blocks, and we generate these extra entities and send them out. We could generate these links which are part of the chain, right? And the other properties of the links are the same as anchors, that they propagate fast in the network because they are just block headers. So these are also block headers plus Coinbase. Right? The Coinbase is just meant to give some sort of financial reward to the person creating them. Right? And or we could create, instead of links, we could instead use this to create anchors, right? And the weight of the chain increases more steadily over time, so we are more robust to the double spend attack. Okay? But for more general attacks, we need a more elaborate analysis, because we have to consider what if an attacker withholds anchors or withholds links or does something fancy like that, right? What new sort of attack can you? Okay, so some of that analysis is in our papers. You can read it if you're more interested. So we will look later in the course at Prism, which was published a couple of years back, and Prism also generates other entities besides blocks, and we look at their scheme. It is much more elaborate than what we've discussed here with anchors or links, right? In fact, Prism has more than one chain. They will actually have multiple chains to deal with the various issues in order to make the main blockchain much more secure.